Gaillardon from University of Utah. Pierre is also one of the organizers, so if you are satisfied, then it's also thanks to him.
If you're satisfied, you come see me. If you're not, you go see Shahar. Thank you, Shahar. All right. Good morning, everybody. Today, I'd like to get us started on reconfigurable logic. There's been many talks about CPUs, domain-specific architectures, neural-inspired computing. Right now, we're going to tap into yet another class of hardware devices. And I have planned a fairly broad set of topics for us for this morning. We'll start with something maybe a little too simplistic initially, but I'd like to guide us through some introductions of reconfigurable logic, more like pretty much a bachelor level intro class on FPGAs and how do you implement logic operations reconfigurably inside of a digital circuit. Then we will look into OpenFPGA, which is an open source project designed to actually prototype customizable fabrics, right? So to go beyond what is traditional reconfigurable logic, but try out new types of architectures, new types of paradigms, mapping different operators and stuff like that. And after that, we're going to go a lot fancier. We're going to look into emerging device technologies that do bring reconfigurability at the transistor, at the device level, and see what paradigm changes that creates. So lots of material. I might have to skip through stuff. Feel free, if you have any questions, just stop me at any time. The goal is to have that as useful as possible to you guys. So let me jump right into reconfigurable logic. So first thing that I want us to look at is where do reconfigurable logic, and in particular FPGAs standing for Field-Programmable Gate Arrays, where do they sit inside of the ecosystem of chips? And here we're going to have a graph showing the performance of the fabric, so compute performance, actually compute per energy type of graph versus flexibility, right? How things are fixed and how much can we play with that? So what we traditionally have, we'll have general purpose processors, right? Just CPUs, very flexible. You just write a piece of code in whatever language, you compile that and you run things, but it's not the most efficient nowadays. At the complete opposite of the spectrum, you'll find physically optimized chips, ASICs, right? Application-specific functions that will be hardwired inside of a chip. And that's what will give you the best performance. You will find right here, some of the advanced machine learning accelerators and that kind of stuff. But you have actually a continuum of options in between, because while on the one hand that could be too slow for many applications, this one will be too costly. So what can we do in between? Well, you have a vast array of options, right? Now, instead of having something fully wired, you can go one step higher and have something that can be programmed through registers and whatnot. Like that's typically a TPU type of topology. On that side, you'll have DSPs, right? So architectures dedicated to better performance while sacrificing a little bit of flexibility. So that's vector processing and whatnot. But if you just continue there, right, you'll find somewhere sitting right in the middle that concept of field-programmable gate arrays that will give you a decent trade-off between flexibility as well as performance. Now, of course, it's not coming for free, right? You'll have to suffer a lot more in implementing your applications than if you were using a general-purpose processor, but it gives you some interesting evolution. And that has been, many innovations happened in the past decade or so, and it's relatively small, yet very interesting market, right? Many applications where volumes are not there yet, performance is needed, are using FPGAs. So now the question that we should ask ourselves is, how do we build FPGAs, right? In this notion of FPGA, we have reconfigurability. So how do you configure a circuit? How do you program a circuit? And more importantly, how do you program a device, right? Because CPUs are programmed. You run that through an abstraction layer, the ISA, right? I will be able to execute instructions. In FPGAs, we're going to wire logic together. But so we need to find ways to program the actual hardwired logic. And how do we do that? We use memories. And we'll use memories inside of a data path. So for example, here you do have an SRAM structure, right, with a traditional latch. So that is storing, one bit of information on that node, and that is going to control the transistor, turning it on or off. And you can, if you change the configuration, you change that path. You can also go fancier with non-volatile memories, right? That would be a flash device that you wire together, so you have one data path, one programming path. In any case, it's finding a way to program electrically one device to be either normally on or normally off, right? And then from there, right, the question that we should ask ourselves is how can we use that type of configuration to implement or to change logic functions? And for that, let's have a first look at how do we implement a logic function, taking a very basic combination of AND and OR function, right? You would do that in an ASIC approach with just logic gates. You'll put AND gates, OR gates, you wire them together. You can also apply some optimization, right? So De Morgan theorem. And instead of using AND gates and OR gates, you can use more technologically friendly logic gates, a bunch of NAND gates in that case, right? But the question is, how can we make this approach reconfigurable? Because right here, everything will be fixed. We're going to use 4 transistors, that's 12 transistors total, and that's it. So what can we do to fix that? Well, an initial approach that was developed prior to FPGA, so the ancestor of reconfigurable logic, was the programmable array logic. Now, here's the idea, right, of a PAL topology. You're going to have fixed logic gates, and what you're going to do is change the configuration, so change the way you wire the inputs and the signals into these logic gates. And to do that, so you had these wide arrays of connections, and you could use memory to program a conductive path between, let's say, input A and that line, right? So you had to configure each of these elements either being off or being on. And to do that, well, guess what? A couple of slides earlier, I showed you how you could implement, right, program a physical path using a memory. So that was the ancestor of FPGAs, very interesting topology, but unfortunately pretty bulky and pretty large, right? Because only a very few logic gates for pretty large overhead in interconnect. So we could do probably better. And that, the key innovation there, not a very modern innovation, right, but was to switch to lookup tables. So now, instead of going with the wired approach I showed you, right, you can take your Boolean equation, you can derive the truth table of that function. Now, how can you implement that? Well, you're going to put a multiplexer. You're going to put your different inputs, and then you just have to connect to 1 and 0s, the various input of your multiplexer, physically recreating a lookup table. So depending on what you decode from your multiplexer, you'll put a 0, you'll put a 1, and that will implement your truth table. Now, if we want to make that static, you're going to use fixed values, so you connect to ground or to VDD, the actual inputs of your multiplexer. Or if you want to make that reconfigurable, you put memories. Now, if you program these memories, you can change the values of your truth table, and ergo, you'll be able to change the function that you're going to have at the output of your lookup table. That's the basic principle of a lookup table, and this is what is used in virtually every modern FPGAs still today. Now, of course, everything we've seen, a lookup table, pretty cool, but it's only limited to combinational logic, right? Modern systems all use sequential operations. So how do we add, timing information to that? Well, we're going to pair lookup tables with flip-flops. So you're going to group together combinational elements, so a lookup table, and you're going to put a flip-flop as well with that. But that flip-flop, you may want to decide if you want to be sequential, so to connect your lookup table through the flip-flop, or if you want to bypass the flip-flop. So for that, you're also adding a configuration multiplexer. So if you configure that memory, you can select either the path coming from the LUT, and by the way, the LUT can be configured as just a pass-through function, identity function, or you can select the path going through the flip-flop and whatnot. That is what we call a basic logic element, and this is the most elementary logic block you'll find in your FPGAs that do support both combinational and sequential logic. But now from there, from that building brick, so far, we're making progress, right? We can configure a basic combinational function. We can also add a flip-flop. How do we make bigger circuits? And remember what I said earlier, if we are not careful, like with the programmable array logic approach, we're going to have a large routing overhead. So how do we mitigate that? Well, we are going to, in the first step, not really mitigate that, but then we'll apply some hierarchy to it. So moving up in the hierarchy from the basic logic elements, you can put an assembly of BLEs and put in front of that some sort of feedback routing. This is, it can be a full local interconnection or depopulated local interconnection, depending on how you want to optimize your resources. But the idea here is that while I have lookup tables and flip-flops, now I want to be able to wire multiple of these lookup tables, cascaded. I want to put multiple of them in parallel. You want to implement various set of topologies for your logic circuit. Yes?
I'm sorry, I know very little about this. This might be a stupid question. How do you decide what was K in your blocks? Because this grows exponentially with K, right?
K, N, I, all these parameters are sizing parameters for the FPGA fabric. There's been plenty of empirical and theoretical studies, well, not really empirical studies, let's put it that way. I need to be careful when I say about theoretical studies here, so completely empirical, based on benchmarking, mostly, to identify what are the best parameters to use. It really depends on the class of applications you're using. The sensitivity on these parameters is not very large, right? So to oversimplify, right, older FPGAs where you want to optimize the area, you use a K equal to 4, so 4 input LUTs. In modern FPGA where you want to optimize for performance, you use K equal to 6. Why 4, why 6? It's also linked to logic synthesis, right? Whatever, n-size LUT mapping that you can do for your logic cones to that, right? So the bigger your logic hardware, the bigger the cones and the function you have to find and map to this hardware. So it's a trade-off. Did I answer your question, actually?
Yeah, sure.
Oh, awesome. Thank you. So now moving to this CLB block, right? So we have some level of routing, but that won't scale very far, right? So you can do that typically, again, n will be equal to 10, right? Between 8 and 10, this is what you'll find in commercial FPGAs. For the numbers of logic blocks put together inside of, so the number of logic elements that you put together inside of a logic block, whether it's called a lab in Intel and Altera's technology, or logic elements in Xilinx, AMD. Now, from there, what can we do? Well, we're going to find ways to implement even more complex functions, and for that, we're going to implement an island-style organization. So now, so far, everything we have done could be fully interconnected or partially interconnected, depending on how you want to optimize things, right? But one thing is for sure, you cannot rely just on that PAL-type feedback, right, with a bunch of multiplexers in front. So with the island-style organization, we'll be able to pack more logic. So you just put an array of logic blocks, and in between these logic blocks, you're going to surround that with programmable logic. So programmable routing, sorry. And this programmable routing will come in different form and shapes. You have a bunch of wires, right? That's your routing tracks. And you have programmable blocks that you will use to either propagate, to route signals in between the various tracks and then connect these tracks to the various logic elements. So what you can already get the intuition of, right, is that we're going to use a massive amount of area just for routing in an FPGA, in reconfigurable logic. So the configuration comes at a very high price. But basically, that will provide us with a way to connect logic blocks and I/O blocks or whatever you have on the periphery. Now, here's the trick, right? You should have complete routability of your system, but you cannot guarantee you can make all the routes at all the time, right? So every single blocks can be connected to another block, but not at the same time, right? So that becomes a routing problem, a placement and routing problem, in order to use the available resources to implement your circuit, right? So the whole game in terms of the toolings will be to optimize, to maximize the resource utilization rates without degrading routability and performance, right? So now these routing architectures, if we start diving a little bit deeper, right? So in between the CLB, as I said, we have the routing tracks. The routing tracks will have some levels of directionality. Some will go, east-west and west-east and north-south, so they're directional. And your switch boxes in between will allow you to connect some of the route to a subset of routes, so it's also not, fully interconnected, right? It's only a subset of that. And then within that, the connection of the routing tracks to the various blocks is also only a subset. So the whole game will be to find topologies and architectures and algorithms that come with that, right? That do maximize routability while minimizing the amount of resources required in the FPGA. This is a really big deal, and this is what makes very big differences between vendors, right? Whether it is Phoenix, AMD, Altera, right? This is where really the differences do shine, and how powerful their algorithms, their tools are to exploit these resources. You can have collections of short and long wire segments. So your wire segments can pass through multiple switch boxes, right? Or they can stop at every switch boxes, right? So it's a fairly convoluted and complicated routing architecture. But the bottom line that everything will still rely on programmable switches. Multiplexers right here, multiplexers right there to connect the various paths and whatnot. In the switchbox structures, there are many different routing schemes that can be used. Disjoint pattern, Wilton pattern, so you have permutation functions that are used to calculate, based on position of your blocks, and get, enough distribution, I guess, of routes. But very, very simply, everything boils down to beyond the architecture, right? If we just look at the low-level hardware, it's going to be, again, multiplexers, configuration memories, and that's it, right? So, so it's really a game of minimizing these resources that are extremely costly, right, at all time. And to do that, one of the techniques that is used is channel segmentation. So if you want to maximize the flexibility of your topology, you want to say, okay, I'm going to only have short wire segment and I connect every switch box. I can configure everything, right? But that will create pretty large delays as well. Resources and delays, because every time you'll move from one CLB to the other, you'll have to pass through a switch box with multiplexers, with buffers, and then you go to the next one. So you end up with very, very, very deep pipelines of logic gates, right? And that will add delay. Yes?
So the CLBs are clocked, is that right?
The CLBs are, the CLBs will contain the logic elements and they can be purely combinational or sequential.
And what about these switching, those blocks, no clock?
No clock.
I see, thank you.
No clock, just signal routing, right? Which creates actually a problem to some extent, right? Because the longer the delay is inside of your routing segments, right, the lower the clock will have to be in your entire circuit, to meet timing. So you want to maximize delay, minimize resources, and for that we're using this notion of channel segmentation, where you'll have short channels, longer ones, and very long ones. Pretty much the concept of highways, right? And local distribution, highway network, long distance, interstate, and whatnot. Same principle, right? So you can take the fast track if you need to go far away, and vice versa. So Now, one item that we have not really talked about just yet, that's this notion of connection blocks, right? So whatever connects the routing tracks to the CLBs, again, a bunch of multiplexers configured, with again memory, right? And the whole idea and the whole trick, once again, will be to identify how much of this connection do you need to the routing tracks. Do you need to connect all the routing tracks all the time to every CLBs? The answer is no. But if you want to support, if the answer is no, you're putting more strain on the programming tools. So that's where, that's where you'll have to be careful with that. That's what we call having depopulation of the routing resources, right? So you can depopulate your routing resource graph, essentially, to save in hardware resources. Now, so we can implement fairly large systems with that, right? So we have our lookup tables, we have the flip-flops, and then we can interconnect a bunch of stuff in between. But as you can imagine, right, if I'm using small lookup tables, right, I will have to put a small lookup table connected to another small lookup table, and I have to go through a bunch of routing resources. That will take area and cost. So what can we do to make the logic blocks more capable on their own, right? We can just make them bigger. So we can move from 4 input lookup tables to 6 input lookup tables. This is a move that people did, but 6 input lookup tables are pretty hard to fill in all the time, right? The logic synthesis tools, the tech mappers, do sometimes have a hard time finding that because of the codes and fan-outs that you have in your logic function and whatnot. So can we still find a way to make bigger blocks and implement small functions efficiently with that without having to zero out a bunch of the inputs? And that leads me to the notion of fracturable lookup tables. That's what you find in every single modern fabrics. Now you'll have smaller LUTs, right? 4 input, 5 input, stuff like that, and some logic in between, multiple flip-flops. So now your logic block can implement either 2 5-input LUTs and 1 3-input LUT, or implement a bigger 6-input LUT. So you do complexify your brick in order to get more flexibility and more freedom for your tools once again. So, and as you can, it's just based on Shannon's expansion, right? You just, distribute a bigger function into something smaller, and you map that into the various LUTs, you recombine things, and you're good to go. Now, that's a way for us to implement bigger functions. But there is one thing that is notably pretty poor, that lookup tables are pretty poor at doing. Those are arithmetic functions. Everything XOR based, right? CMOS is pretty bad at doing that. The reason, and we'll look into that later, right? That's because of the nature of the transistors, right? They are inverting by nature, right? So it's very easy to implement NAND NOR types of logic, but XORs, majorities, very hard. And multiplexers, being based purely on these transistors, are no exception, right? So they will be relatively inefficient to implement anything of carry chain type of logic, right? Adders where you have carry chain and whatnot. So what is being done is that you're going to complexify further your routing and logic elements in order to support what will be your limiting factor in arithmetic function. And this limiting factor comes from the very long critical path you will have in adder function with the carry chains. Right? If you think about an adder, right, you'll start with your carry input, and then it goes through a first stage, and it ripples through. There are many different architectures to avoid that ripple carry type of topology, using carry look ahead and a bunch of different, but in principle, right, you are going to have a very long critical path that you have to deal with. And if you just implement that in regular lookup tables, well, you'll put that in your lookup table, then you have to route through a bunch of resources to the next stage, and that will cost you immensely. So what is being done is to implement specific. So that's what I said, right? So if you have to implement your routing, your carry, you will have to either go through intra-routing, or inter-CLB routing. Takes a lot of time. So what we're doing here is that we're adding specific circuits inside of the CLBs to deal specifically with this arithmetic carry chains and similar stuff. And so the specific carry pass is based on a propagate generate rewriting of the full adder, where your sum depends on the propagate function that you can get, and then this is a typical full adder based on that principle, right? So you're going to calculate the propagate signal. Then here you can decide with a mux if Cin should go through or not, and then you calculate the rest of your sum, right? Now what is interesting here is that you can take this block, you can hardwire part of it, put another part of it in the function generator, in the lookup table, and just augment your fracturable CLB with these carry control signals. And these carry controls right here will have the multiplexer to propagate the carry and the sum calculation, while that initial propagate calculation can be implemented in the lookup tables. So that way, with minimal increase of the area of your CLBs, you can implement these critical arithmetic circuits using dedicated path for C in and C out that will not use the standard routing, but that you will use dedicated hardwired high-speed paths for computation. So this is pretty much where we stand with these modern logic element architectures. And now that create that concept of multi-mode logic blocks, right? So these blocks are getting pretty complex, and they can implement multiple different functions, whether they are standard LUTs, whether we are using the memories as a RAM, whether we use all the registers and the flip-flops as the shift register, right? So these blocks can be seen, through different set of goggles, depending on what you want to implement. So on top of that, you have large multiplexer support, soft multiplayers, a bunch of different stuff, right? So the question would be that these blocks are now very versatile. How do we efficiently use them? And that's where EDA tools will have to come into play. But before we look into that, now this is what a modern FPGA structure looks like. Where you will recognize all this island-style fabric, right, with your logic blocks, your routing and whatnot. You'll have, of course, at the periphery a bunch of IOs. But some of the things we have not talked about would be this kind of block. So if you just have these logic elements, that's what we call an homogeneous FPGA array. But as you know, right, computing and implementing sequential and combinational logic is one thing. It's very good, but it's not enough. You need to be able to deal with memory, larger amount of memory if you want to implement, cache operation, if you want to implement, whatever, registers, if you want to implement a CPU, that kind of things. But also, you need to consider higher orders of arithmetic functions like multipliers, fancy DSP operation, and for that, we are actually including heterogeneous blocks inside of the fabric. So here, memories, DSPs, and again, you're going to now not make an homogeneous island-style fabric. You're going to make that fabric heterogeneous with different types of blocks and different natures, so you can support all of that. So, an example? Oh, I'm sorry, yes. Yes, thank you.
Let's go back to the previous slide.
Yes.
So first question is that the number of CLB in this figure is like in the same correct order of magnitude of real-world FPGAs, like a few hundreds. Is that the case?
No, it's actually a lot more. It's modern FPGAs will have
thousands, millions?
Millions.
Okay, millions of such stuff in a 2D structure. Okay. The second question is like what type of RAM is that? Is that SRAM, DRAM, or?
That would be SRAM. So SRAM, so everything that FPGAs do, right, are based on logic processes, right, because you want to have that as small and as optimized as possible, so they use the latest and greatest tech nodes, right, and it is very hard to implement a DRAM or flash or other things, right, anything that is exotic, right, onto an advanced digital node, right, so everything is SRAM based, pure transistor, logic transistors based.
So what you just mentioned is that we can kind of treat the LUT as RAM, but here the blocked RAM is kind of a denser version of
Denser
real
version, like really if you think like of a memory macro. Yes. Yeah. So everything of these blocks can be programmed to be logic functions or memory as well. We call them LUT RAMs. But as you can imagine, they're not very dense because they do other stuff, right? So for something where you'll need, some good density, so cheaper memory, essentially, you will rely on the actual BRAMs, block RAMs, BRAMs. Okay?
Okay, thank you.
Thank you. DSP blocks, right? What is the most highly demanded DSP operation that you can find in modern application? That will be a MAC operation. Everything will be convolution-based and whatnot will be using MAC operations. And of course, multiplication, accumulation, right? So you do need a multiplier, you need an adder, and you need some registers, right? All things that can be implemented with LUTs, but with a bunch of routing overhead. So let's try to avoid that routing overhead and provide an actual set of dedicated operators, like in that case, just an optimized hardware multiplier with some flip-flops in front, right, to pipeline things correctly. And that's what we're going to put inside of our FPGA as the multipliers, DSP types of structures, right? So again, it's always a game of finding what is the proper resource that you need to use to implement inside of your fabric. And now, while we have a very nice hardware platform, right, we need CAD to support these various blocks. And I'll pass on the details here, right? But that's where you have to take your entire arsenal of techniques from high-level synthesis to logic optimization, logic synthesis, tech mapping, and then physical design, packing, placement, routing, all that kind of stuff. So you do use these resources. So now that's something that is very important, that you need to consider very carefully the design of your CAD tools alongside the architecture. You can have the best architecture in the world. If your CAD tools are not supporting that efficiently, it's completely useless. So there is always a fairly large co-design step that is done to implement these FPGAs efficiently.
So I'm not sure I entirely understand. Physical design is what you had in the previous diagram, the blocks with the multipliers and the memory and all, right?
So that would be the hardware design, yeah, the hardware platform, whatever is being implemented. What we call physical design, right, that's the tools steps that will take a given application, right? The logic synthesis, you map that to existing primitive. You know that I want to connect lookup tables and DSPs and stuff like that, right? The physical design step is to identify which of these logical parts should be mapped where, and then how do you configure the actual routing hardware.
Got it. Thank you.
Thank you. So now with that, right, hopefully that gives you a decent idea of what an FPGA architecture and topology is. Now I'd like to go slightly deeper into the practical aspects of that through the OpenFPGA project. So the OpenFPGA project, that's something that we do in my lab. And the general idea of that project was initially, can we academics, right, easily do architecture exploration of FPGAs? And the answer is yes, we can do that. There are several tools that help you do that. But if you want to really consider the hardware aspect, the implementation aspect, that becomes a lot harder, right? Because you need large team of engineers, and what can we do for that? Now, beyond that, it's also it's particularly appealing to evaluate FPGA and to modify FPGAs to modern workloads, right? And many of these FPGAs are designed for general purpose logic, right? So they are good at implementing everything, but they are not super good at anything special, right? Can we find ways to improve the FPGA architectures to shine, in some domain-specific applications? And that was the idea of this OpenFPGA project. Can we, replace this very cumbersome process that is used by the industry, where you have, like your complete specs and whatnot. You have some senior architects. It splits into two very large teams: hardware engineers, software engineers. The hardware engineers come up with a super cool architecture and make it real, right? Make the silicon, while the software team implement the supporting tools. can we do that? Actually, that was a pretty bold move. Can we do that with one person, one student in one day and replay that entire process? That's the whole point of OpenFPGA. And to do so, we took a software-centric approach. So interestingly enough, right, the first part of my presentation has focused only on the hardware. And I just had one slide telling you that, oh, well, and the CAD tools, need to support all of that. We took the exact opposite approach. What we did was actually creating a supporting software that will be generic enough, right? So placement, routing, synthesis, the whole thing, right? That internally models any type of FPGA architectures you want through some high-level modeling. This is the topology I want, right? If your tool is capable of internally representing the architecture and generating routing resource graphs, then it becomes pretty easy to just dump this data structure, dump the topology of that fabric that you have described, and then go through the physical implementation. Not as simple as that, because you need to think about a bunch of physical design aspects, right, on how to place and route and physically implement that piece of silicon, but that's the idea. So we have a unified code base in OpenFPGA for fabric generation, design verification, and end-user bitstream generation. So in other words, I can model any types of FPGAs, I can represent them internally, I can map applications to that, I can generate configuration files for that fabric, and I can also manufacture that fabric, physically, implement that fabric on silicon. And so that's a pretty convoluted slide, but in principle, there are a couple of blocks I'd like to highlight. So we have some input sections where we're trying to do everything on a fairly high level with an XML language. You just describe the topology you're interested in your FPGA. We have that engine that helps us take this high-level description and actually implement an actual chip out of that. That's what I call the XML to GDS. GDS is the file format used for manufacturing of the chips. That's what you send to a foundry. We have the verification part to make sure that whatever you are going to manufacture is going to work. And then you have the bitstream generation, which is what the end user will see, right? You put application, and then you get the bitstream you can configure on the rest of the machine. So essentially, OpenFPGA supports a very wide set of different topologies, from very complex, very modern types of topology. You'll recognize some type of structures I showed earlier in the presentation. And I pass on the details of everything it supports. But in principle, here it is, right? So you do have your FPGA array. You have your different blocks. Again, you recognize like some sort of a modern type of logic block. And what we do is that we have this high-level language that we use to describe what we have. So for example, right here, we say, well, OK, this multiplexer that you use to select between your flip-flops, so your sequential and combinational path, right? I showed that earlier. This multiplexer, I want that to be implemented with a one-level multiplexer structure. It's a hardware thing, right? You can have one-level, two-level, mux tree, so different ways to implement a multiplexer. And I'm coming in as a designer and say, well, this brick should be implemented that way. Same for like configuration chain. Now, all these memories, I want them to be programmed using this brick, and I want them to be structured in a scan chain, whatever. I pass on the hardware details, but the idea is that you can describe whatever you have in your topology, in your architecture. Now from there, the tool can go on its own and generate the actual internal representation. It can generate bit streams. I'll pass on these next two slides. But what is pretty interesting and important is that it can, from that high-level representation, implement your entire chip. And it does so. We had to introduce several innovations on the physical design of these chips because we want to use standard chip design techniques, and FPGAs are pretty unique compared to regular chips. They do have a large number of individual instances, so that hits the scalability of the placement and routing algorithms. They have combinational loops that are not programmed initially, right? You do program them during the operation of your FPGA, but if you look at a structure of an FPGA netlist, it's a bunch of loops all over the place. That makes the tools fail miserably. So what essentially we did was to come up with a strategy where you can design very, very, very small fabrics, so you can implement your various blocks in context, and then you simply do a Lego-style top-level assembly of taking these blocks, replicating them on larger fabrics, and they're designed to very nicely, abute together. I'll pass also on many of the aspects here in the interest of time, but essentially, right, with a system like OpenFPGA, you can implement very large FPGA fabrics. That's just an example. 160K LUTs, right? So that's a mid-range type of FPGA, not a very, very, very large, but mid-range, in less than a day, right? Fully automated, and that's the interest here of using such methodology. So now, if you are trying to explore new types of structure and types of topology, you can now very quickly prototype things, understand the impact of these new blocks on the actual performance of your system, and quickly iterate through that. So we have done many chips using this platform. That's the first one we did, 12 nanometer chip. We did a bunch of open source stuff as well. Very interestingly, each of these chips are using a RISC-V CPU plus an eFPGA, and they were done from project start to tape out, one student for 1 month type of efforts for each of these chips. So you can really prototype things quickly. I'll pass on the details, but that's one thing I'd like to highlight about why such a framework is interesting. This is some of recent work that we have done, not published just yet, but now we started asking ourselves, instead of using just traditional FPGAs, right, that we certainly can do, right, is there new bricks we can put inside of FPGA that will benefit modern workloads? And in modern workloads, right, like AI engines, AI applications and whatnot, people like to implement systolic arrays, right? So simple processing elements, so you can move weights and computation into different ways, right? And calculate convolution in an efficient way, that kind of stuff. So we asked ourselves the question, can we implement specific primitives inside of an FPGA that will be helpful to support systolic array type of hardware and implement that inside of an FPGA structure. So that's what we did, and so you just create your systolic unit, you put that in slices and whatnot. The integration with OpenFPGA is very easy. We just add one more block inside of our XML, you push a button and you get your full fabric. You of course have to make all the supporting toolings that will come with that, right? From how to use these primitives from a high level, and how does it map to the hardware. We can talk about that, but in principle here, what is important is that by implementing by adding this kind of bricks into the FPGA fabric, we can significantly improve area, power, max frequency, and whatnot for some modern workloads. It's just an illustration of how trying to identify the what missing primitives could be inside of an FPGA fabric, implement that, and make the architecture evolve could be beneficial for many of the modern applications. Okay, now it's an open source project. I invite you to go and have a look into that. It's on GitHub. Lots of documentation. Never enough documentation, but at least there is an attempt at documenting things. So I encourage you guys to try that. Now, I'd like to switch gears and go to the last part of this presentation, and I'd like to venture into now bringing reconfigurability not at the architecture level, as we did so far, but really at the transistor level. Is there any alternative to conventional scaling? Everything we have covered, right, so far in this bootcamp has been, Moore's law, Dennard scaling, this is cool, I make things smaller, and I can pack more transistor, I can do fancier stuff with that. But, and that's essentially, right, the technology push, right? That's Moore's law, but there has also been a market pool that's, adding multi-core CPUs and, finding these two tricks, right, to push chip design, right? Either you make the technology better or you make your architectures better and you push things along. And the motto for that has been, for the past 4 decades, increasing the number of devices per area unit. If I can increase the number of devices per area units, I can either make things smaller, that's my tech push, or I can make more complex architecture, multi-core CPUs. One of the things we started exploring was, can we increase the device capability for a given area? So in lieu of making things smaller, business as usual, right? We make things smaller and we put more. Within the same area budget, can we have our devices that can implement more stuff, more exotic stuff, and can we use that, right, to our benefit? And that's what we call functionally enhanced devices. And I'm going to show you one embodiment of such a device. And it's a device that does not use doped source drain CMOS. So I don't think we really went into device topology and device physics just yet in this boot camp. I'm going to try to venture there, right? But modern transistors, right, are based on semiconductor, right? So silicon or silicon germanium or whatever, and you have the gate control around that. It's electrostatic doping, right? And we're using FinFET topologies. It's moving to CFETs and a bunch of different structures. But the idea is that, such as nanowires, right? So you have even better control. But the idea is that in modern devices, you have what is called an ambipolar conduction. So you have both N-type and P-type carriers, electrons and holes, inside of the device. And the whole point is to try to control that. And we control that through doping. So we make sure that, now we're going to force and put a lot more electrons, right? And that's going to be an N-type device that will be a normally off device, right? And that's what we want to use. And it's, of course, the more you advance in geometries, right, the harder it gets to properly dope your transistors, because we're talking about a couple of nanometers of dimension, and we're talking about the statistical process of implanting dopants into the silicon. So you end up at reaching the physical limits where you only have like a handful of dopants available in your source drain regions, and there's a lot of variability, and it's a problem. So our approach, and the industry does very well at controlling that, by the way, right? So it's not really like a fundamental limitation just yet, but we try to think outside of the box, and instead of killing that ambipolar behavior, can we control it? Can we rely on that? Can we use that? And we came up with that multi-independent gate structures. So now we're going to use electrostatic doping in additional gates to control the doping level inside of these different regions and change the conduction of the device. And what is interesting here is that with a single device, we have been able to demonstrate and achieve 3 different modes of operation, depending on the gate polarization, which is a dynamic reconfiguration of the device polarity. So changing the device from N-type to P-type on the fly, and I'll show you why it could be interesting. We also have a dynamic control of the threshold voltage, so you can change the properties from high performance to low power, essentially, dynamically. And also having a control of the steepness of the transistor, what we call the threshold slope, right? So it's how steep does that device switch, and that leads to interesting properties for analog operation and RF operation, and we'll briefly look into that. So we build these devices. I'll pass on how it was done, right? But it's actually pretty interesting devices. Professor Demichelli from EPFL, who will talk, I believe, on Friday, did a lot of that, right? I was in his lab before, so that's something we did together. Pretty fancy academic device. I pass on the fanciness of the device, and let's look into the actual control. So now here's the idea, right? With our device, now if we took a helicopter view of it, we have a central gate and we have 2 additional terminals, the polarity gate at source and drain. And now these polarity gates can serve as controlling the polarity of the device. So if we look at our symbol, right, if PG is equal to 0, we'll have a p-type device. And if PG is equal to 1, we can have an n-type device. How does that work? I don't know if you're really excited and interested to look at Venn diagrams, and none of us are probably interested in that. But the general idea is that by changing the polarity, you can change the conduction bands of the region near the source and drain, and therefore, create Schottky conductions of either electrons or holes, depending on which side your bands are lowered. So I'll pass on the details here, but here's where I believe it's getting pretty interesting. Now, if we just look at our device, right? So we have the control gate, we have the polarity gate, and now, as I told you, if PG becomes 0, we have a p-type device. If PG is equal to 1, we have an n-type device. So now let's try to make a circuit out of that. And we'll start by making a very simple and stupid circuit, just putting a pull-up resistor on top of that device, right? And we're going to put 2 logic signals on both gates, A and B. So on the control gate and polarity gate. If B on the polarity gate is equal to 1, that device will be an n-type, and it will act as an inverter, right? Conversely, if B is equal to 0, it's going to be a p-type device, and it will act as a buffer, as a follower, right? Now, granted, very poor control of the signals because we're using pseudo-logic. We're also using a PMOS device in the pull-down network. That's not what we should do. So, degraded signals. But now, let's try to apply our circuit tricks and find a topology that will allow for always not having pseudo-logic, but having complementary MOSFET type of structures, and also finding a way to always have a PMOS in the pull-up network and an NMOS in the pull-down network. Just standard circuit design. What happens right here is that we're going to restore our logic levels to where they should be, and that's pretty nice. But now, if we look into that, and I just told you, well, we do have, it's a programmable inverter / buffer with 4 transistors and a bunch of gates. Not super exciting, but if we try to understand what that implements, it's actually a 2-input XOR. It's a 2-input XOR realized with only 4 transistors. And that has to be contrasted with what you would get with a CMOS logic implementation, right? In CMOS logic, you would have 8 transistors to implement the same functionality. These transistors have to be sized differently because these N-type and P-type devices do have different conductions, and so you need to account for that. So that's precisely the illustration I wanted to make about increasing the functionality of the device rather than scaling it. We arguably do have a much bigger device. Now it's a device with 3 gates that we have to control, right? It's taking some area on silicon, but you will need less devices to implement the same functions. So the device is more capable for a given area, and that leads to some interesting gains. Another type of functionalities that we have been able to achieve with these transistors is now, in lieu of controlling my 2 polarity gates together, right? I can start having, and that's what I have with 1 and 0s. I can have different modes where I'm going to move my control gate to different terminals, right? So now, essentially, I can use my control signal to pilot the Schottky barriers or the control gate, right? And that will change the device properties, especially the on and off current that you can achieve and that kind of stuff. I will spare you guys from the actual Venn diagrams this time, but here is some interesting result that you can get, right? With these devices, with the same device, right, but different control, now you can really play with different VT values for your transistors, turning it on earlier or later, and having different leakage levels essentially. But not only you can have a dynamic control, right, of that threshold. What is also interesting is that you can use that property to create new logic gates as well, or more powerful logic gates. So that's, for example, our 2 input XORs. By the way, we can also create a 3 input XOR. This slide is actually pretty poor because we do have ways to implement NAND gate with only 3 transistors using the other stuff. But I pass on the details again. What is important here to understand is that intrinsic behavior of the devices can be used to create quite a few interesting logic gate structures, not typically achievable with CMOS. So that's the case here. I always like to highlight these 2 input XOR gates. It's also true to expand that stuff to compact full adder implementation, right? So now implementing the sum, implementing the majority for the carry using the same type of structure with only less transistors. But there are many other circuits, right? We looked at compact NAND gates, we looked at flip-flops, we looked at asynchronous logic elements, embedded power gating, so a bunch of different stuff that you can do with that. Now what we did here was to try to understand and to benchmark these kind of technologies with other competitors, I guess, for modern implementations. And it's going to be a very busy graph, right? But essentially, it's using a well-known methodology in the field called the BCB methodology from Intel. Again, the details are probably not so important, nor the results, actually. But what is interesting here is that we do get to a very interesting performance point, right, with these devices, not because of the density that they can achieve, but because of the functionality. And I like to show that with that slide that I think is more, it's more interesting to compare essentially the origin of benefits from using these functionally enhanced devices, and it's actually not coming from the device. So let me guide you through that. So for a given circuit, implementing in CMOS devices, we'll have a normalized energy delay product. That's value 1. If we were to replace all the CMOS transistors with individual functionally enhanced devices, we get a 17x penalty there. And large penalty because these devices are bigger, bulkier, Schottky barrier based, so they have less ion current, right? So you just degrade things big time. But now you can start applying all the different tricks I showed you, right, at the circuit level. Now, if you implement novel gates with 2 input XORs, well, guess what? You reduce area, the overhead by 2. You also have, the full adders. You can reduce that further. Now you start getting a gain. Because of the way you implement your gates and topologies, it becomes very cheap to use dual rail logic, for example. So you can also change the way you implement your architectures, and that gives you an additional gain. Then you can also jump to more modern materials that are almost impossible to dope today, right? Like 2D film transistors and devices that are expected to push beyond Moore's law, right? So and are very easy to control because they're ambipolar, right? So if you start compounding all this gain, this is where you start seeing some benefits. And also a couple of interesting things to note, right? Because of the compactness of the gates and the new routing architectures you can come up with, right? You also reduce the length of your wires and therefore parasitics. So the gain starts compounding beyond just the device, right? So if you just look at the device level, it's not extremely promising, but it's really when you start looking way beyond that stuff. Now, very briefly there as well, I'd like to talk about an even more exotic behavior that these devices can implement. It's called the S4 effect, the super steep threshold slope effect. And now we are going to use this polarity control type of behavior. And I apologize for showing you again a Venn diagram, but now this time we are going to use this electrostatic doping to bend, push the bands even further. So you can create a region where the electrostatic field will become pretty intense, and when carriers will go through, they will start having some weak impact ionization and essentially having some carrier multiplication in the device. And that will help turn on the device faster. And essentially, you would end up with transistors that can turn on super, super quickly. Traditional transistors are limited in the slope, right? So that's called the threshold slope. It is typically above 60 millivolts per decade, right? So it takes some time for a transistor to turn on, right? But using this kind of principle, you can have devices that do switch very, very quickly. The community has been chasing these kind of devices for a while with the idea that if you can turn things on very quickly, we can reduce the VDD, right? Instead of having to stay right there when it's nicely turned on, you can reduce VDD there. And reducing the voltage, reducing the power consumption, right? So it's power consumption, dynamic power consumption is a quadratic relationship with voltage, so you win there. It's not expected to be the case very much with the devices because you still need to have fairly large voltages to bias your gates, but nonetheless, you get very, very, very steep behavior. And that steep behavior, even if you cannot directly rely on that to reduce VDD, has very interesting applications as well for RF or for analog devices, right? Because your transistor will have a very, very steep gain right there. And that gain can be used to either make a terahertz detector, so you get very sensitive detection, or you can also create analog circuits with a much larger gain compared to what you would have with standard MOSFETs. So now I'm branching out beyond computation here a little bit, right? And I apologize for that, but again, that's where I wanted to highlight that some devices might have different properties that are worth exploiting in many different verticals, right? Rather it is to make more powerful computation or branching out to different detectors and whatnot. The last point I'd like to cover in this presentation is where EDA needs to come in. And that's probably where that will touch more your typical interests, right? But it's everything we do, we have to design with these transistors. So we need to find ways to model them. We need to find ways to exploit them through theoretical representation and manipulation of Boolean functions. And because the performance of any modern digital circuits depends strongly on EDA tools. And logic synthesis has always been a CMOS supporter, right? It's been designed because MOS transistors are good at implementing NAND gates, NAND and NOR. Therefore, all the tools have been exploiting that. So the data structures are based on that. The algebra that is used in these tools has been based on that, right? So it's designed to implement NAND, NOR multiplexers. That's why I said, earlier that CMOS is very bad at implementing arithmetic functions. XORs, majority, the tools are terrible at dealing with them as well. Because we don't really know how to do that, so that was pretty easy. Or you want a multiplier, here is a multiplier coming from a library. Don't touch it, and you should be good to go, right? But can we go beyond that, right? Can we actually disrupt this model? Can these novel technologies and computing paradigm disrupt this model? That's what we've seen with these new transistors, right? They are very, very efficient at implementing XOR gate and majority gates. So can we find ways to support that a little bit better? And so a couple of years ago, we came up with a majority-based logic optimization. And we started looking into median algebra and majority logic, right, as a generalization of AND and OR, right? So with a majority gate, you can, bias one of the inputs. You'll get an AND, you'll get an OR, but you also get your majority, right? So can we use that in representing logic functions? And this is a full adder represented in a Boolean network of AND and OR gates, what you typically find in logic synthesis tools, right? Now, if we were changing that representation, you only get 2 nodes instead of a bundle of nodes. And can we manipulate that further? And that's pretty interesting, that was really created to deal with these controllable polarity devices. So how to manipulate majority logic? So we came up a couple of years ago with that concept of majority inverter graphs, where you have a logic network consisting of 3 input majority nodes and regular or complemented edges, so very similar to an AND inverter graph that you have in modern systems. And you do get a direct transposition, of course, from an AND or inverter graph to a majority graph, where you can just replace and tie to 0 or 1 the various inputs. So because you have this direct transposition, right, MIGs do include AND or inverter graphs, and MIGs do include AND inverter graphs. Lots of research was done on AND inverter graphs, and by default, right, this majority inverter graphs will be at least as compact as what you can do with AND inverter graphs, but we can probably find better ways to better representation and unlock new representations. So to manipulate these graphs, we came up with an axiomatic system with a set of 5 rules: commutativity, majority, associativity, distributivity, and inverter propagation. That basically algebra is sound and complete. So there is, and that's not the case with N inverter graphs, right? So with N inverter graphs, there is, it is not guaranteed that you can reach optimality of a design, but with majority inverter graphs, it is guaranteed you can get there. Of course, getting to the optimal representation is an NP-complete problem. So it's still not guaranteed that we can actually do that, right? But but at least the representation is very powerful, and we came up with a set of recipes to optimize these graphs for area, delay, and power. So now what was interesting is that we came up with this concept of majority inverter graphs to support these modern devices, but we have also used that to implement a system with just CMOS logic. And with CMOS logic, it's a 3D graph representing delay, area, and power for some benchmarks and comparing commercial tools, and inverter graphs, open source tools, and our majority technology. And we just beat performance of all these tools pretty significantly. Now, majority inverter graphs are part also of commercial tools, right? And it's been really remodernizing the way people approach logic synthesis. But that's nonetheless, right? I wanted to make that quick note, right, around that, right? Is these emerging technologies can make us rethink how we approach, some of these Boolean network manipulations, and come up with clever techniques that surpass whatever is done today. So clearly, EDA, and I will generalize that, right, to any theoretical work, right, should not be, just a supporter of what technology can do, right? But it should be at the core of the problem, right? And then really helping co-designing systems and whatnot. And what we have seen today, right, with this, with this type of device, does apply also to different nanotechnologies, to memories, to neuromorphic computing, to a bunch of different stuff. So if there is one thing, and when we started actually thinking about that program, right, with Siemens, I believe I mentioned that on our first call with Char and Kirk, right? Doing something around majority could be pretty exciting. I still believe it's the case. And I'm just, giving that to you guys as food for thoughts. With that will conclude my presentation. I'd like to just thank all the students involved and the sponsors, and I'll be happy to take any questions.
So when you talk about, this majority, you said, designing the minimum number of gates, and then are there other things that you're concerned about, like the depth of the circuit or the fan? Is it just the number of gates, or can you talk a little more about that?
So that would be So you're essentially worried about three things, right? That will be the number of gates. So I'm talking gates, right? So that's, what I showed you was mostly a graph representation. After your graph representation, you need to tech map that into gates, right? But let's talk about gates. Number of gates, because that will be linked to area. Depth of your logic pipelines, so in between flip-flops, because that will be linked to delay and performance. And to some extent, switching activity of your individual nets, because that will be linked to power. Right? So depending on your logic that you're implementing, you might have nets that do switch more than others, right? That can switch every single time if you put XORs versus NANDs or stuff like that, right? That will be linked to power, essentially. So you want to minimize, so you want to be able to extract from your graph representation these high-level metrics, right? So number of nodes will be a decent proxy for the number of gates, right? The depth of your graph will be a decent proxy for the depth of your logic levels. The activity factor of the edges in your graph that you can calculate based on the primary input activity factor and percolate that through the logic function in your graph would be a good proxy for power. And then you try to minimize these three parameters, right, with different weights that you apply to one of them, essentially.
Okay.
Does that make sense?
Yeah, that makes sense. Thank you.
Thank you for a very interesting talk. Regarding this majority function, are you hoping it'll give you like better than constant improvement, or are we talking constants? Are you hoping that you can take n, CMOS gates and replace NAND gates and replace them with, say, n divided by log n of these gates, or are you just hoping for half the number of gates, or what? Like, what's the expectation here?
Yeah, this is interesting and unknown. So what we've observed and what our general intuition expectation is, right, is that by using majority inverter graph optimization and whatnot, right, apply to standard CMOS. Let's not change the technology for a second, right? It's been giving us 2-digit percentage improvements. Right? 2-digit percentage improvement, like,
Okay, right.
up to 30%, things like that, which is significant in logic synthesis and in CMOS, right? And we expect that to continue to grow, but it's adding 2% here, 3% there, and just keep improving, right? But there is a limit. Where it gets particularly interesting and exciting, I believe, right, is when you consider a device change. Right? Now, if you have devices that will natively implement a majority function, like these devices I showed, right? Like ReRAMs, like spin logic, a bunch of different stuff, right? Then all of a sudden, these devices can bring you a multi-X gain, right? Not so much maybe coming from the use of majority, but because majority is their native representation, and therefore you will introduce them without the overhead that you would do otherwise. Does that make sense?
Sure.
So yeah, so that's so now to answer your question, right? The expectation is 10, 30, 35% for regular CMOS technology. If you introduce new technology, 10x, 15x, 20x, something like that.
This is with regards to the earlier stuff with OpenFPGA. I'm trying to understand the overall use case, because you're not only, you see, it seems you're also synthesizing the FPGA.
Yes.
But what if I want to use an off-the-shelf FPGA? Do you have libraries that essentially? Do you have specs for those in OpenFPGA?
So we do have some architectural support in OpenFPGA for existing commercial FPGAs. There are other projects that are using the similar set of tooling that is compatible with OpenFPGA that you can use also for that, but it's limited, right? And it's limited because the FPGA manufacturers will provide you with the design tools. They are pretty powerful, And now closed source, of course, right? So with OpenFPGA and associated tooling, VPR uses and whatnot, it's interesting because you can explore existing fabrics and be more innovative, maybe on the tooling, right? So that there's some advantage. But that's it. Now OpenFPGA is really designed to help you co-design or co-explore architectural modifications of the FPGA topology alongside the supporting tooling. So that's really where, why it is designed, for that. And it could be, using new exotic technologies as well, emerging memories and whatnot. It could be implementing new types of blocks inside of your FPGA. It's really to create, to explore that concept of domain-specific FPGAs. Not general purpose FPGAs as what you can get, from the industry today, but really customizing things towards specific, specific use, being AI, being control, being radio, being defense applications. They will always have some different needs for like more DSPs and more AI and more memory, and and you can really play and serve that wave essentially to improve your overall system.
And is that a common use case where I mean, like the technological support exists for me to ask for my own customized FPGA board to be made? Like, will it be competitive in performance with the ones that commercial customers?
Yes. So that's the whole point of OpenFPGA, right? And I scratch the surface, especially in the physical design. How do you implement these chips, right? Because it's maybe less of the interest of this audience, right? But the whole point of FPGA was to create all the optimization, so whatever you get outside of that framework will be as competitive as getting a commercial FPGA. It will be a lot more costly because you have to manufacture that, right?
So I was asking, what is the manufacturing cost for one of these? Like, are we talking just a few $100,000? Are we talking tens of millions?
It depends on the tech nodes that you're using, right? So the chips I showed, right, the 4 chips, I was showing you, right, they were based on open source technologies. And it's basically, the full tape out is $10,000 with test boards, packaged chips, and you get like 100 or 200 of these chips, right? So not cheap, but relatively cost efficient, right? For doing something, on a fancy, modern technology node that is commercially relevant and whatnot, right? So OpenFPGA is used by many commercial companies, in the US and abroad. That will be in the $20 to $30 million to get like a very, very fancy commercial fabric, large size, advanced technology node and whatnot, right? But that's nonetheless something that it's possible to do with OpenFPGA that was not possible to do before, right? I should have mentioned that, but OpenFPGA was funded by DARPA, right? DARPA, the DoD, had the problem of needing some custom FPGAs for RFCOM and that kind of things. They cannot get these custom FPGAs today. They actually sponsored some programs with the big FPGA vendors, but now these products were very costly, outdated now. So how do you keep that edge, right? So that was really designed for that. Reducing the non-recurring engineering cost of manufacturing custom fabrics.
Maybe we can continue this during coffee break here. Let's thank the speaker again.
Thank you.
So the question I get is that, okay, so suppose that I'm a